Hey everyone, welcome back to the Foundry by Forge College. You absolutely crushed your capstone project summary, and now, well, it's time to level up again. Today, we're cracking open Solana's state storage architecture to look at a massive piece of the puzzle called Cloudbreak. We're going to figure out exactly what it is, how it works, and why, if it didn't exist, the entire network would basically throw a tantrum and grind to a complete halt.
Here's our engineering blueprint for today's explainer. We'll start with the state storage problem, introduce Cloudbreak, hit its three core responsibilities, trace the transaction pipeline, break down some actual code, and then wrap it all up.
All right, Section 1, the state storage problem. Let's start by visualizing the absolute disaster that would unfold without a highly specialized storage system. Imagine a giant, bustling warehouse factory. You've got thousands of workers sprinting toward the exact same filing cabinet at the exact same time. It's like Black Friday, but for paperwork, right? People are crashing into each other, files are dropping, and everything completely stalls. In database terms, if you don't manage this and reduce that cross-thread contention, you get a massive traffic jam and incredibly high lock overhead. So the million-dollar question is, how do we store and serve a massive amount of accounts while letting everyone access them in parallel?
Which brings us to Section 2, Introducing Cloudbreak. Enter our hero, which is essentially the ultimate hyper-efficient warehouse management system for our validator node.
Now, what's fascinating here is what Cloudbreak actually is not. It's not the runtime executing the smart contracts, and it's not the networking layer. It's a highly specialized accounts database layer. It actively maps account state across memory and disk so that massively parallel validation can actually happen. It keeps all those metaphorical warehouse workers happily in their own lanes so they never ever bump into one another.
You probably remember how proof of history acts as Solana's deterministic ticking clock, giving us the ordering and a perfectly predictable slot timeline. Well, think of Cloudbreak as the system that eagerly consumes that timeline. It uses it to perfectly coordinate exactly when different parts of the account state become durable and how they are retrieved during slot processing. Moving right along to Section 3, 3 core responsibilities. To keep this factory running smoothly without becoming a critical bottleneck, Cloudbreak handles 3 massive jobs.
So how is the workload split? First up is partitioning. This assigns accounts to specific physical shards or buckets, totally eliminating worker collisions and reducing contention. Second is indexing. This maps a public key to its exact location and version, basically acting like a real-time GPS so the validator can locate files instantly. And finally, lifecycle management. This cleans house by creating snapshots and pruning old, obsolete versions, meaning the validator can start up lightning fast without drowning in old data.
Okay, Section 4, the transaction pipeline. Let's actually follow a single transaction through the validator's warehouse to see these responsibilities in action.
It's a precise 5-step dance. Step 1, slot assignment. Proof of history tags the transaction. Step 2, the read phase. Before doing anything, the runtime asks Cloudbreak for the latest account views, and Cloudbreak uses its index to grab them instantly. Step 3, execution. Updates are temporarily staged in memory, so we don't clog up the disk right away. Step 4, the commit, where updates are officially written across different shards. And Step 5, background tasks kick in to clean up, create snapshots, and compact the data.
Now let's hone in on Step 4, the commit stage, because this is a fascinating engineering balancing act. Cloudbreak constantly tunes a trade-off. Do you use synchronous durability, making sure every single write is instantly saved to disk? That's super safe, but agonizingly slow. Or do you use batching, grouping writes together? This massively improves throughput, but it does leave a tiny window where data could be lost if the system crashes. Cloudbreak smartly navigates this by batching writes per partition and prioritizing those snapshots we mentioned earlier.
All right, Section 5. Breaking down the code. We know the theory, so let's actually look at the engineering blueprints to see how accounts get assigned to their storage shards in Rust.
Under the hood, the mapping absolutely has to be deterministic, meaning the exact same public key will always equal the same shard. To pull this off perfectly, the system uses a uniform mix, kind of like a 64-bit Fowler-Nolvo hash. I know, that sounds like a massive mouthful, but all it really does is evenly distribute the load. By doing this, it completely prevents hot shards, which is that disaster scenario where way too many active accounts end up crowding the exact same physical disk space.
And here is a totally brilliant choice by the devs. The code uses a mathematical technique called modulo reduction instead of simple bit masking. Why? Well, bit masking only works well if your total number of shards is a perfect power of 2.
Modulo reduction is kind of like dealing a deck of cards evenly around a table. It guarantees a perfectly balanced assignment even if you're working with an arbitrary, weird number of shards in a real deployment.
Which brings us to our final section, wrapping up Cloudbreak. Let's pull this all together and tie it back to the broader Web3 concepts you're exploring in this program.
Here are your 3 big neon sign takeaways for the day. First, partitioning isn't just about keeping things tidy, it actively aligns physical storage with parallel execution threads so they never collide. Second, versioned indexing is absolutely essential to guarantee you are always reading the exact slot-correct version of an account. And third, lifecycle management directly controls how fast a node can boot up and join the network.
Ultimately, Cloudbreak isn't just a basic database or a simple key value store. It really is an operational subsystem. It is the beating heart that makes Solana's parallel execution physically possible, deeply tied to the threading of the validator itself.
So, as you step into your next module on the core components of Cloudbreak storage, I want to leave you with this question to chew on. Where exactly do you expect to find the underlying code for these partitioning and indexing mechanisms? Think about it. Be sure to visit forge.college to dive deeper into this subject and discover a ton of other incredible Web3-related educational resources. Keep that momentum going, and I'll catch you in the next explainer.